Howdy folks, welcome to week 5 homework. Today we're going to be looking at multiple regression. I know we've done regressions with multiple independent variables so far, but what we're really going to be covering are all the special options and choices you have when you run a multiple regression. And the cool thing about these options is that they actually let you answer some fairly sophisticated research questions. So let's go ahead and get started. Take a quick look at all the regressions that we've learned so far, that we will be learning. We've learned dummy variables, which are when you do a regression and you have an independent variable that is categorical, you kind of fake it into being a continuous variable. We've done multiple regressions with multiple independent variables already, and we've looked at the regression formula where you can predict a dependent variable, you can predict a y given the coefficients and data for any given x or a series of independent variables. So we've looked at logistic regression as well. Logistic regression being a regression for dependent variables that are categorical, so making a prediction, what is the likelihood of this or that condition. And these next 4 types of regression are things that can apply to any of the things that we've learned so far. So any of these options are going to be useful, applicable in logistic regression, or with dummy variables, or with your regression prediction formula. So what are we going to be looking at? We're going to take a look at what forced entry is. Pro tip, forced entry is basically just the type of regression that we've done, the type of multiple regression we've done so far. We're going to look at hierarchical regression. The quick and dirty there is that hierarchical regression allows you to choose to give some variables a more liberal analysis than other variables. Then we're going to look at blocked regression, which is the same as hierarchical regression. However, it's done in groups of variables, so you can have multiple like bunches of hierarchical levels. And last we're going to take a look at stepwise regression. Stepwise regression is a cursed, forbidden type of analysis. I'm going to let you know what it is and kind of how it works, but we won't work through how to do it. If you'd like to learn how to do it, I might just briefly show you in SPSS if we have time, but it's not a particularly appreciated type of analysis in the literature, so we're not going to focus a whole lot of time on it. The only other thing that's not on this list is we will look at what interactions look like in your regression. So that seems scary, it seems confusing, it's really not too bad. Let's get started. Before we go on to these next couple of slides, I'd like to bring up just a slide from this past week's class. So to understand how these things are going to work, it's important to understand how a regression actually happens. So if you have multiple independent variables, here's blue circle independent variable 1, yellow circle independent variable 2, red circle is our dependent variable. Well, the covariance between one variable and another, that's going to be the significance for that independent variable. So this overlapping part of the blue independent variable is going to be compared to the remaining dependent variable variance to come up with significance. This is kind of your baseline correlation. But when you have multiple independent variables, you get unique covariance for one independent variable, unique covariance for another independent variable, but you're also going to get this shared covariance here. And how is significance evaluated given these different conditions? And what even is this last part here where you have covariance between the independent variables? Let's break it down. Number 1. Theoretically, your independent variables should not be related. So any covariance between the two is ignored in the analysis. Furthermore, any covariance between the 2 or more independent variables and the dependent variable, this shared covariance section, is ignored. It's ignored in the analysis, once again, because your independent variables are supposed to be independent. If it was not ignored, then we would have an assumption problem. So we've got these three parts here, the two unique covariances and unaccounted for variance in the dependent variable. To assess the significance of independent variable 1, the unique covariance for independent variable 1 is divided by the unaccounted for variance of the dependent variable, and that relationship dictates how significant IV1 is in predicting DV. Same thing happens with IV2. Only the unique covariance between the independent and dependent variable is compared to the remaining variance in the dependent variable to estimate a significance. How much does independent variable 2 predict dependent variable? Now, let's take a look here at an example. We're going to skip this slide very briefly. That shows what happens when you run a regression that involves two independent variables. This is an example that I really like. It starts off with a very simple premise that's obviously flawed. Taller people have shorter hair. Now the real relationship here is that females are shorter and females have longer hair. They tend to have longer hair. So it's kind of a third variable problem. But if we only look at these two variables, we're going to get a significant relationship that isn't necessarily true. And so this kind of highlights how a regression can look significant, it can have a high effect size, and still steer you in the wrong theoretical direction. That's why it's always good to try and include a bunch of covariates. So let's take a look at that data. I'm not going to release this data, it's just an example that I've used in other classes, and I really like it. It's just some data I made up. I can show you how I made up the data. It's not too complicated if you are personally interested. So we're going to work with these first three variables: the height of the person, the hair length of the person, and whether or not they're female or male. I think female is 0 here. I don't remember. So let's do the regression. Go to regression, linear regression, and we're going to pop in our independent, dependent variables. Here's dependent variable. Sorry, here's independent variable. I just did them backwards. Here's independent variable, your height. It's a covariate because it's continuous. And our dependent variable, hair length. Let's look at our results. We get an R-square of 0.685. That is monumental, amazing, huge, gigantic, crazy, exciting. I would fully expect there to be a significant F-test if we checked. And there is. Okay, great. Let's take a look at the coefficient. For every 1 point increase in height, we have a 0.8 decrease in hair length. So every inch that you are taller, you have 0.8 inches shorter hair. And that is a significant coefficient. If we go look at the standardized coefficients here, what is this standardized estimate going to give you? I've called this an effect size for the coefficient estimate over here. So this would be B1 and this would be beta 1. What is this number and why is it different? This number here is in the scale of the original variables, so inches of height and inches of hair length. This variable is in standard deviations. So what this is telling us is for every 1 standard deviation increase in height, we will get a decrease of 0.8 standard deviations in hair length. The fact that these two numbers are very similar tells me that their standard deviations are very similar. And we can just go and check that real quick. So let's pop these variables into a descriptive thing. Standard deviation. Standard deviation for height is 2.597. For hair length, 2.545. So this is a slightly smaller standard deviation than this one was. So this is a slightly bigger relationship than this. There's been very, very few instances where I've seen or heard anyone describe what the standardized estimate is, like actually tell you, so there you go. It's in terms of standard deviations. All right, back to the regression analysis. Let's pull up a scatter plot that's going to show us this relationship. If you go to the graph making option here for the regression, it's going to give you just the regression line, but this doesn't show us the data. So it's not as helpful as you might want it to be. We're going to use the scatter module here in Jamovi. So if you haven't gotten, you can go to the available and install it. Here's what it's called, SCATR. And it's really helpful, just a quick visualization of what's going on in this regression. So again, we're going to put in our dependent variable hair length, y-axis, independent variable height, x-axis. We're going to get a linear regression line. This is the same linear regression line that we have over here. The scales are a little bit different, but you see it goes from 10 down here to ends at about the 80 mark. So this goes from about 10 down here, ends at the 80 mark, so it's the same line. So what's going on in this data? You can clearly tell that this is a, well, what sort of assumption is going on here? Might want to pause. 3, 2, 1. This is a heteroscedastic result that we've got going on here because there's a lot of more variance here and here than here, so it's not giving us the same amount of variance in our prediction line. You would see this in the residual error plots. If I can show you that, let's go to the residual plots. So here we go. Here's this. It's showing you that there's fair amount of residuals in this area, fair amount of residuals in this area, no residuals here in the middle. And that kind of, as it goes up in this beginning part, the residuals get smaller. Can we see that here? Yeah, sort of. There's definitely wider residuals in this area than it is in this area, but the real obvious part is the fact that this is not random. Again, not random, so problematic. The same problem is seen in those other graphs. Okay, so what else are we looking at here? Well, I know and I can tell you that this is data from girls and boys. The girls have longer hair, boys have taller height. And so, yes, there is a negative correlation going on here. Yes, there is a significant, strong thing happening. The taller you are, the more likely you are to have shorter hair. But let's look at what happens to our regression when we add in the better predictor, the excuse me, the categorical gender variable. So our R square increased, and it's always going to either increase or stay the same if you add variables. P-value didn't really change, but we can't really see what happened because it's so significant. I don't remember what the F was, but I'm fairly sure it would have gone up as well. Let's take a look at our coefficients here. Now, height is no longer significant. The estimate for height went down from 0.8 to 0.17, so pretty teeny now. But instead, the female-male variable is significant, and it's got a huge estimate and a bigger standardized estimate than height used to be. Why is that? Understanding what happened there is the most important thing to understand for these complicated sorts of regressions. Let me show you what happened in the scatter plot. Of course, again, we can look at this graph over here, but this really, it ain't telling us the story. If we add in the female-male variable, this is telling us a little bit better of the story. Over the course of the height variable, there are just two completely different regression lines that we have to take into account. So I guess females were 1 here. Are they? No, females were 0, and so their hair length is higher. Males were 1 here, and their hair length is lower. And over the course of height, the taller you are, you tend to have longer hair. But this doesn't really tell us the relative significances of these, and the scatter plot doesn't help either. So if I was to go back, I can tell you that the height variable is not significant. So this height thing going on there is not significant. Let me show you this with the data. That's going to make this million times easier to understand. So we had that relationship before. Now we see, if we include the female-male variable, that females have a hair length that maybe it's positively correlated to their height, but what really matters is that if you're a female, you have a higher, longer hair than if you're a male. And again, males, maybe taller males have longer hair, could be something going on there, but for the most part, if you look at those data, it looks like this line is pretty flat and these guys are kind of randomly distributed. So in this case, we have this independent variable 2 accounts for the variability over the course of one variable and the dependent variable. So what's gone on here is that the overlapping parts for this, the female-male variable overlaps a bunch with height and a bunch with hair length, such that height has very little significance, very little unique covariance left over, but hair length and gender are still pretty big. So if I was to show you a graph of that, it might look, I can't really adjust it. Let's just do it in paint. Do a quick paint thing. It might look something like this. So here's our independent variable. Here's our height variable. So there is overlap and it was significant before. And here in green, we'll do our gender variable. So it's going to look something like this. The size of the circles doesn't matter. More so what matters is that here's the here's the unique covariance of gender, which is not spelled with an H. Here's the unique covariance for height. Here's the dV, which was hair length. And so this shared covariance, the majority of height's predictive value is lost in this regression, which makes height not an interesting variable. This is all it's got left. But gender's looking pretty good because it's got a fairly sizable unique covariance. Okay, one thing I'd like you to note too. When you add independent variables, sometimes they'll become more significant, sometimes they'll become less significant. Because this remaining part here, this remaining unaccounted for variance, got smaller. So even though the height portion got smaller, it's compared to a smaller bit instead of what it was originally being compared to, this bit here. So what matters is that relative difference, which is going to be kind of funky. It's going to depend on your variables. There's not going to be any consistent result there. Okay, back to our current stuff. So if I was to summarize here, the gender variable overlapped with the height variable so much that it removed the height variable's significance and became significant itself. Say that again. The gender variable overlapped with the height variable so much that it removed the height variable's significance and became significant itself. I can prove that there is a substantial amount of overlap between these two in a couple of ways. We can check the collinearity statistics. Remember that a VIF of 10 is bad. 10 or greater means that you have too much relationship in your independent variables. This 7 is okay for the assumptions, but it does tell us that height and gender were pretty related. If I do a ANOVA to just check, okay, is there a relationship between gender and height? Yep, there's a relationship there. In fact, it's a pretty big one. So we know that those two are pretty strongly associated to each other. Not strong enough for it to be an assumption problem, but strong enough that that including one variable is going to affect the other variable pretty substantially. Rightio. Let's get back to the PowerPoint. Really, this slide should come next. So this week's homework, we're going to be working with these different types of multiple regressions, and they allow you to choose to allocate shared covariance. Remember, there's like a little bit here where the yellow and the blue overlap. This shared covariance bit, you can choose to allocate it to a variable. So it's kind of like saying, independent variable 1, we're going to put you in the regression first. We're going to give you all the chance that you can possibly have to be significant to make our model good. And then we'll add in independent variable 2, and it's just going to get as much chance as it can in the same way that it would normally in a forced entry regression. So you see that independent variable 2 is a little bit more strictly, a little bit more conservatively handled. Independent variable 1 is going to be a little bit more liberally handled in this version of the regression. And this is what shows you this is a hierarchical regression, where you hierarchically give one variable or multiple variables sort of precedent or first dibs on the dependent variables relationship than the other ones. Here's kind of the SEM sort of relationship we were talking about there earlier. We're going to be learning more about mediational relationships in a future class, but if you wanted to draw out a diagram for the relationship we saw earlier, yes, hair, sorry, this is kind of backwards. Height predicts hair length, but the better explanation is that gender predicts the two, and you kind of have to wonder, is there really a relationship there? Well, there is sort of. There is this kind of mediational relationship. We'll look at that in the future, but we're going to focus here on this part here. Sorry for that aside. Let's see, what do we have on this slide? Standardized coefficients are an STD scale. We already talked about that. P-values for individual variables can and will change as you add in other independent variables. So we just saw that in this multiple regression with hair, and gender, and height. Whenever you add in a variable to regression, the coefficients are going to change, and they can change pretty erratically. It's not always a very good idea to try and compare coefficients or even standardized coefficients between regression models unless the model is almost exactly the same, because one coefficient is never going to be devoid of its relationship to the other coefficients in that same model. Most of the time, your coefficients, your standardized coefficients, are pretty much, well, your coefficients are just for the regression formula. Your standardized coefficients are just for comparing the relative value of independent variables to each other. You can try and make comparison between regression models, but I would not advise it unless you know what you're doing and you really understand this stuff. Why would a independent variable become more or less significant when another variable gets added into the regression? That's this part here, these bullet points. If a variable becomes more significant when you add in another variable to the regression model, it's likely because there was less residual variance in the dependent variable and not very much overlap with the new independent variable. So if we go back to this slide here, whatever we added in didn't cause a lot of shared covariance, but it definitely reduced the unaccounted for variance. If a variable becomes less significant when you add another independent variable to your regression model, it's likely because there was a substantial amount of overlap that it added. So it added a substantial amount of shared covariance, which means the original first variable lost some unique covariance, and that shared covariance that it added was greater than the lost unaccounted for variance, so the relative difference is lower. I know that is confusing and complicated. When I first learned this, I really had to go and draw out the diagrams over and over and over again myself. So take your time, watch this over again if you need to. The important thing to know is that when you compare coefficients, it's rough, I already said that. Oftentimes it's best to compare r squared or r squared change. Looks like this video is getting a little bit long, so I'll hurry it up here. Let's talk about blocked regression. Blocked regression is the same as that hierarchical regression, but you can do it in groups. Let's show you both of these things here. I'm going to use, well, let's start off with the attitudes data set. So I'm going to go to Open, Data Library, our data sets, attitudes data set. I'm just going to show you what happens with a bit of a hierarchical regression. So you see I've already kind of done some stuff here when I was preparing to do things. We're going to run a regression. Our dependent variable is going to be rating. Let's try and predict rating from just all these other variables. If you would like some background on what these variables are, these are surveys, evaluations about people in a company. So what rating did they get on their evaluation, and this other information, how many complaints, how many complaints have been received about this person? Does it seem as though this person has undue privileges? Do they seem to learn quickly? Have they gotten raises? Are they good at critical thinking? How well have they advanced in the company so far? So that doesn't matter. What matters is what is the relationship here between, what is the difference between that hierarchical and forced entry regression? So right now we've got a forced entry regression. We go grab the model fit and the coefficients, standardized estimate coefficients here, just so we can look at those. And we're going to focus here on, we're just going to look at one variable. I'm going to pick a variable that has a lot of overlap with the others. So most of these variables are not significant. If I go my assumption checks, collinearity, the highest collinearity is with the complaints, no, the raises variable. And so raises here is a very not significant variable. So let's do this same analysis, but we're going to do it hierarchically, and you'll see the differences. To do that, we're going to go to the model builder, and we're going to add a block. And we're going to take all of the variables except raises, and we're going to say, raises, you get all the opportunity to be significant first. So what does that do? Raises didn't become more significant, but instead we got this extra line here in the model fit and a model comparison thing here. What's going on? Well, let's click here, pick model 1. And so model 1 is the regression with only raises as an independent variable. Raises is significant when you put it in by itself. Its standardized estimate looks sizable to me. The coefficient is decent. I don't know what the scales are here, but importantly, the R square, 0.34, not ginormous, but pretty dang good. Significant p-value. What is this model 2? Model 2 includes, watch this bit here, all of the regression variables. And so this looks like a forced entry, because now raises is less significant, and we know that must have happened because there's a lot of overlap between raises and the other variables, which means it's lost a lot of its unique covariance. We know there's a lot of overlap because we checked the collinearity statistics and found that raises had the most collinearity, the most shared variance with its other independent variables, which means that it's not a surprise that it became apparently less important, because it lost all of its unique covariance to shared covariance. How does this differentiate itself from a normal regression? Two things. Number one, you can report this coefficient table and this coefficient table. So you could say, when included by itself, raises is a significant and substantial predictor of rating. However, when incorporating or accounting for other independent variables, raises loses its unique predictive value. What numbers are we going to attach to that? How can we prove that raises was a good variable? There's not really a good effect size overall here. This is for relating to other independent variables. What we can look at is this R square. And this R square is pretty good. The addition of those 5 other variables improves the R square by 0.384. Delta R square means R square change. So the difference between Model 1 and Model 2 is an improvement of 0.384 R squared, which is substantial. This is a significant improvement. If we look at these two things, this is a significant model. This is also a significant model. So we can say that, yes, raises significantly predicts rating. However, when included in a model with all these other variables, raises is not as important as something like complaints. And we know that because this p-value here. How important is complaints? Well, we could add a new block and put complaints in by itself. So now we've got 3 models, and we see that the improvement from Model 1 to Model 2, how much better is complaints and raises compared to just raises? We have an improvement of 0.336. How much better is all of the variables compared to just complaints? We have an improvement of 0.049. So these guys didn't add a whole lot, but complaints did. And maybe we can even switch these two and see if complaints is the majority of the show. And we do see that. First model is 0.681, and it doesn't improve a whole lot. You can see here it doesn't improve a whole lot. So by doing this analysis, by moving the variables around, we can see that complaints is really the variable driving the explanatory power in this model for rating. But we can only do that by messing with the hierarchy of the relationships there. Again, this is a confusing topic, and it really takes a bit of playing around to get it. Notice that if we look at the models, the significances of things are not higher or lower because we put them in this certain order. They are when we don't include everything else in the model, but what we can really look at to see, did this variable matter over this, or did this block of variables matter over these two, are the changes in R square, and the changes or the significance of these changes. So adding raises did not significantly improve our model. Adding privileges, learning, critical, and advanced did not significantly improve our model. This demonstrates both the hierarchicalness, hierarchy, and the blocked regression. We're already at the 32-minute mark, so I will just very, very quickly go through this last 2 things. Number 1, what is a stepwise regression? We just talked about how you can play around with your regression variables to find the most significant R square and the most substantial variables. A stepwise regression is going to mechanically go through every possible combination of variables, blocks, and hierarchies to find the most minimal and substantially significant model you can. Basically, it's going to try everything it can, and whatever seems to be the best is going to give you that model. Stepwise regression is not advisable because this method of try everything out is not backed by any sort of theory. Whenever you play around with your hierarchy of variables, theoretically what you should be doing is including them in a hierarchy based on some sort of theory. For example, you may want to say, we're going to put all of our control variables in the first block, and then all of our demographic variables in the second block. And the third block is going to be our variables of interest, so that the R square change from the variables of interest will be over and above those other sets of variables. There's a theoretical reason to include that hierarchical order. If you ever do a hierarchical regression or a blocked regression in your analyses, it is strongly encouraged to clearly state why you made a hierarchy that you made. You can explain it in just about any way, and people can always tell you that they don't like that relationship or that they do. Oftentimes reviewers will say, well, what if you only just included one variable or one model? What if you did your hierarchy this way or that way? And while that is technically a little p-hacky, it's technically kind of harking or searching for relationships, I'm not going to pretend like that's not something that everyone does all the time. And when reviewers give that to you, if your advisor gives that to you, most often it's easiest to just give them what they ask for. Try what they asked, see if it matters. And in honest actuality, the information you get can be useful. You just have to be wary that you are trying things out randomly and you're giving yourself that possibility of type 1 error. Okie dokie. Okie dokie. Last bit, and I promise this will just take 5 minutes. Sorry the video's gone a little bit long. Regression interactions. An interaction in an ANOVA is a situation where you look at multiple independent variables so that you can identify their relationship to the dependent variable in a more complicated way. To say that more particularly, or in another way, an interaction allows you to observe the relationship between an independent and dependent variable when accounting for particular conditions of a third variable. The relationship between variable A and dv depends on variable B. That's a moderation, that's an interaction, and interactions will work in exactly the same way in regressions. Let me show you that. We're going to use the air quality data set. And I've already kind of done this analysis here. I'm not going to walk you through how to do the interaction. Never mind, I will. When you pop these variables in, we're trying to predict ozone in the universe based on wind and temperature. Bear in mind, by default, no interaction is included in this model. So you go to the model builder, click on wind, temperature, and you click on this arrow, it adds in the interaction. You may also click on this drop-down arrow if you want to deal with more complicated interactions or only add in main effects or what have you. So we've got here the regression model without the interaction. I'm going to go put this interaction here in this block too, and we'll see what it does. Adding in the interaction improved the regression model by 0.05 r². Not a whole lot, but significant. Let's see what this looks like in a graph. I went ahead and did a slightly different analysis here, which will allow us to take a look at the data. Do we need the data? No, we really don't. I'm just going to skip that. Let's just look at the interaction here with the estimated marginal means dialog. Pop in wind. All right. So as wind increases, ozone decreases. You can double check that here with the estimate. Wait a second, did I just say that wrong? As wind increases, ozone should decrease. Why is this 14? Well, let's see if adding in the temperature variable will explain this better. There we go. That explains things better. So, here's what the interaction says. As wind increases, overall, ozone decreases. Here, we have a representation of the temperature variable. In reality, temperature is going to fluctuate this slope in a continuous way, but the graph gives us temperature at -1 standard deviation, mean temperature, and +1 standard deviation. So, when temperature is low, wind does not affect ozone as much. When temperature is high, wind affects ozone a lot. How do we read these coefficients? As wind increases, ozone decreases. As temperature increases, ozone decreases. Sorry, as temperature increases, ozone increases. Gosh, I'm making this confusing. Let's try again. As wind increases, ozone increases a lot. As temperature increases, ozone increases a bit. But, and here's the big but, when you multiply wind by temperature, the ozone decreases for every 1 point of wind times temperature. And this looks like a small estimate, and this looks like a small estimate, but bear in mind, we're dealing with the two numbers multiplied, so these numbers are going to be way bigger. So that's how we get to this graph. Wind increases, ozone decreases, particularly as you got this stuff. It kind of gets complicated, but at the very least, I hope you can see how the interaction here is just showing you a more complicated situation. Wind accounting for temperature for ozone. Last quick thing I'm going to show you, something I mentioned in a previous class, just as kind of a proof of concept. An interaction is, in essence, just the independent variables multiplied. So if I go over, I'm going to multiply wind and temperature, add a variable, computed variable, call it W by T, and let's just say this variable is equal to wind times temp. There we go. So we see that the wind times temperature variable is really large compared to either wind or temperature by themselves. That's why the coefficients seem little. Now, let's, instead of adding in the interaction, we'll add in the interaction we made and look at the relationship. You're going to want to compare this with the previous thing that we were looking at, but you'll notice that the results are fairly similar. And I don't think that this graph's really going to work here because now we have a bunch of different relationships. But I'd like you to just kind of an extra thing, compare what did we just do to our relationships, to all of these numbers by adding in the wind times temperature fake, false interaction. And oh God, I know what it's doing. It's making, I don't know what it was doing. I don't know why this was crawling sideways. That's enough for this video. Hope you have a good week and take it easy, y'all. Let me know if you have any questions or concerns. I know this is a complicated topic and we went through quite a bit of stuff pretty quickly. So I'm sorry if you have to watch this video 100 times, but I know that you will thoroughly enjoy my silky smooth voice. So ta-ta for now.